Good morning, Sensei. Ohayou gozaimasu.
Classroom.
Good morning, sir.
Okay, ohayou gozaimasu. Good morning, everyone. Professor Izumi, let me start. Okay.
Do I start?
Yes. Okay. I will start now. Bismillahirrahmanirrahim. Assalamualaikum.
Your screen does not appear yet.
Yes, Dr. Yuda.
The screen is your screen is not appeared yet. I mean your screen. Screen nggak kelihatan, Bu Diana?
Yeah, yes, not yet, Dr. Yuda. I will opening this lecture. Okay. Thank you for coming, Professor Izumi, or Izumi Sensei, and then also Professor Dr. Iman Rahayu, our Dean, Professor Iman, and then also team teaching this lecture, Dr. Yuda Prawira Budiman, and then Dr. Iwan Kurnia, and then also Dr. Rustaman, and all participants here also in our room. There is our students. This morning we will continue the WCP program, and this morning we can hear lecture from Izumi Sensei. Here topic is photocatalysis. Before Izumi Sensei start a lecture, let's me introduce again maybe some of lecture on also our students not yet joined last Tuesday. Wait a moment. Okay. Let me introduce Professor Izumi. Okay. Professor Izumi birth is January 4th, 1965, and then academic degree, Doctor of Science, University of Tokyo, and then experience research in Stanford University, California, 19 1996 until 1997. And then field of study, surface chemistry, environmental chemistry, and then X-ray spectroscopy. Professor Izumi graduated from bachelor in the same university, University of Tokyo, and then master also the same, and then continue Doctor of Science at the University of Tokyo. Job, April 1989, Asahi Chemical Suzuka Factory, and then continue as research associate in Tokyo Institute of Technology, and then also Izumi Sensei get the scholarship from Monbuso or Max Research Fellow in 1996, and then lecture at Keio University also, and then still July 2007 as associate professor, Department of Chemistry, Chiba University. And then finally got the professor, the same in Department of Chemistry in Chiba University at April 2019. And then committee, societies, and activity, Professor Izumi, many visit as a reviewer, also member of research reviewer at American Society of Chemistry also, and then as reviewer some of journal in Japan and also outside Japan. Also, Professor Izumi as prize, Young Scientist Prize, and then Fujino Prize 2000, and then also Special Lecture Prize of Young Generation 2001, and then meeting, international conference, and some of prize belong to Professor Izumi. And this one original paper, I think this is not all paper has report here. Here around 1905, right? 1905 paper has published Professor Izumi and member of the lab Professor Izumi. And then also finally Professor Izumi published some of books. Nah, this one. Okay. This book promoting effect and hydrogen spillover in supported selenium rhodium cluster catalyst. And then also this book I want to tell you about this book, this one, because Professor Izumi published this book with my professor, Professor Anko Sensei, this one. And then also the other book, Professor Izumi also published this topic, state selection of low concentration of element, etc. This is also with my professor, Professor Anko. This Professor Izumi and also my professor, Professor Anko, still published together for in journal, also in my book. Okay, I think it's Professor Izumi, now time and screen yours.
Okay. Good. To choose. This is my screen. I think this is today's topic. And I see classroom, wide classroom. And Diana-san, thank you for introducing in detail for my CV. And today, Diana-san, one of the one of the session of the WCP Diana-san program.
Yeah.
Today I talk about synthesis of inorganic compounds, photocatalysis. And I did not know what kind of the audience attend to this. And Diana-san announced me her students, graduate students, attend today's lecture. And Tuesday, I suppose the researcher, the Diana-san friends, was mainly attending, and I did not intend to prepare the lecture for students, so educational, and I just considered the talk in continue to the how to write good papers. So, but I think I will try to explain in basic point of view, maybe good, because Diana-san students may not be necessarily be all person in the field of photocatalysis, I think, or in the field of inorganic chemistry or physical chemistry. So I try to explain in general point of view, but as the nature of this talk, it tends to be research basis. So please try to follow this. Research in my group, and also with the background of the world research trends. So this is the title. So inorganic compounds talk, but in connection to photocatalysis, and also investigation of photocatalysis is talked. So I start with this. If I know to talk to students, I may prepare to the introduction of Chiba City or Chiba University, but I'm not prepared because Diana-san and Anita-san visit us next week. So I've not prepared for that. Unfortunately, I'm sorry. So for students. So I directly start to talk the synthesis of inorganic compounds in connection to photocatalysis. So inorganic compounds talk, maybe it's very wide fields, wide range. So today's talk, the major topic is trial to fabricate excellent inorganic compounds for photocatalysis. So, and as a nature of this research, this is correlated to tomorrow talk. Diana-san called tomorrow talk is the workshop section 2. So Diana-san may suppose the Tuesday and Friday is the coupled session, and today is the intermediate educational session. I suppose so, but I'm not familiar with the whole sequence of the WCP program. So I in my point of view, today's talk is correlated to tomorrow's talk. So if I do not know, the students has time for tomorrow, but today's talk itself is, I think, something educational and I think helpful for your study, I think. But the tomorrow correlation for tomorrow's talk is today is so synthesis and the preparation is taught, but we always analyze the sample, analyze the photocatalyst and characterize it, hopefully under the photocatalytic reaction condition. So feedback is obtained to make better one. So this arrow means the analyzed and the based on the analysis, better one can be made. Further improvement is done. So its talk is continued. But today's talk itself has some conclusion. So, and this is Diana-san kindly introduced the paper, our papers, the original papers especially. And this is the previous paper. So, and on my website, if you need report to Diana-san for your credits, you can check. And Diana-san is recording, so maybe available somewhere, today's talk. And this is the paper published. And this is, for example, this is synthesis and similar shape of zinc oxide, crystalline. We may call it crystal, but this is very small. This is the length is about 20 or 30 nanometer, width is 10 nanometer. Size of zinc oxide crystal is grown by some condition. And this is previous our report, and zinc oxide is mixed with copper ion. And this catalyst is CO selective oxidation we used. Beginning. This is electron microscope image. This is enlarged picture of our crystal. And the size, this is size, the 100 nanometer. This bar is 100 nanometer size. So that's the reason I say this crystal mean size is 30 nanometer length and width is 10 nanometer width. Histogram is not shown here. In paper, it's shown. And see, so, and we, in this shape, this is electron microscope. This is scanning electron microscope, but we also use the other techniques. Technique is tomorrow's talk, so I do not talk. It's mixed up and confusing for you, so I do not tell almost nothing today for the analysis, but many analyses were used. So copper was analyzed. Copper metal anion was analyzed also, and also molecule vibration. For example, CO bond vibration was analyzed. And based on this, see this picture, widened picture. This is the top part of this spheroidal shape of zinc oxide crystal. Okay, so this is top position. So here is top position, like here, top position here. Hopefully you see my mouse movement. I do not know. And this is edge position. So edge position is like here. All the crystalline seems relatively similar shape based on the controlled synthesis condition. So this is inorganic compound synthesis, basically. And edge copper exists around this position. I'm sorry. I come back. And this is, we assume, based on analysis technique, we assume what is happening in when we supply CO gas and oxygen gas, but also in the dominant hydrogen gas, because we wish to purify hydrogen gas. Hydrogen gas is clean energy. Hydrogen gas is used, no carbon dioxide is formed. So, but hydrogen gas is formed from, for example, from petrol. Hydrogen gas contains CO. CO is hazardous to your what? CO is not what? Why it's not good for in the hydrogen gas? CO is not good for your fuel cell. Your fuel cell is damaged very, very soon. So CO need to be removed. So this is the intention, CO here. I apologize, too small picture. This is paper, directly from paper. So CO and oxygen comes. And in the abundance of hydrogen gas, H2 gas. So CO comes here, this formate species is found on the surface here. And then light is irradiated. By the irradiation of light, Diana-san also know well. Diana-san is studying, for example, titanium oxide. Her study originates from her study, PhD study in Osaka. Osaka is the west city in Japan. And Diana-san obtained her doctoral degree there. And that is titanium dioxide. This is similar in organic oxide, zinc oxide. This is very white color, bright color than titanium dioxide. And by irradiation of light, UV means ultraviolet. So it depends on wavelengths, we call UV light, and visible light. UV light sometimes not good for your skin, but not always. So UV visible light is irradiated in zinc oxide, electron and hole. Hole is the positive charge. So electron is -1. So hole is +1. Because material must be always 0 in total. So electron is -1 charge. So when electron go into copper ion and reduce copper, for example, something companion needed. That's hole. So hole is the imaginary charge. So essentially that is the positive charge in net positive charge in this case in this solid inorganic material. So hole go to this direction. So hole oxidize hydrogen. Hydrogen oxidized forms proton. And this is something like proton in your aqueous solution, but this is on surface. Photocatalysis is taking place on surface. So proton is formed. And oxygen comes, oxygen O2. Oxygen molecule comes here to copper. We investigate the interaction of copper and oxygen by spectroscopy. And HO2 is formed by supplying hydrogen to O2 on surface on copper. And then next electron and hole is generated, and then proton moves on this surface again. So at this section, top section and edge section for each synthesized inorganic compound. So H2O2 is formed. So then when after proton moves transfer to this O2 species, CO2 is formed because CO comes and coupled with the oxygen of hydroxy. group, CO2 is formed. CO2 is removed from hydrogen gas and it can be easily separated. Not damaging your fuel cell. A damaged fuel cell means it damage your platinum. So platinum is still needed for most of the commercial fuel cell used at the present condition. And HO2 moves to split to 2-hydroxy, forms the original catalyst condition. So this is catalysis. So catalysis is move a circle, and catalyst itself reacts, but catalyst comes back to the original position and repeat the same cycle. That is the definition of catalyst. And this needs light irradiation, not heating. So this is called photocatalysis. And photocatalysis is, in many cases, advantageous for sustainable application because it does not need thermal energy. So light energy, if you use the natural light, it's sustainable. The sunlight is almost eternal. So we can make the photocatalytic reaction the sustainable way. So this is the possibility of, Professor Ampo was also doing such reaction. I cite Professor Ampo group paper in this paper, I remember that. So CO is selectively oxidized. Hydrogen does not react on this catalyst. Hydrogen remain unused for the hydrogen energy, like your hydrogen. So then, this is explanation I already done. And so in some summarized equation, CO and OH, surface means the surface of zinc oxide, and hole plus charge forms CO2 and proton. In summation of this picture. Okay. This is on the top. Okay. Yes. Sound is somewhat delayed, but hopefully it's okay. The internet, I think, reaction issue. And O2 on the edge is reduced to hydrogen peroxide, but it's split to 2-hydroxy group. You may wonder why hydroxy is here, but zinc oxide, it's very normal thing. For this zinc oxide and also Diana Sensei, titanium dioxide, or even other metal oxide, transition metal oxide, like aluminum dioxide is not the semiconductor, but also silicon dioxide is used. It's not semiconductor, so cannot be used for photocatalyst, but what else? Tungsten oxide. These oxide, we try to choose high surface area, specific surface area sample. And in other words, the very, very fine powder. And so, if so, you try to make zinc oxide high surface area. The particle, one particle is, the size is very, very small, like this 10 nanometer or even smaller. So by doing this, surface is very low coordination. Low coordination means easy to react. If you make greater crystal, like this side of crystal, it's thermodynamically, it's very, very stable. So surface, and the ratio of the surface is becomes smaller, much smaller. If you make this side of crystal, zinc oxide crystal, so it's inert, does not behave like this photocatalyst. It's do nothing for CO oxidation almost. So we try to make smaller crystalline as this. And by doing this, the surface is low coordination. Low coordination means in one sense. So zinc is here and oxygen is here, and zinc is not coordinated well. So it is on surface, zinc is naked. Zinc cation is naked. So it is react with water in air. So with air, water is H2O. So for example, zinc surface, I've not written the picture. Zinc oxygen bond exists on the surface because it's zinc oxide crystal. But when react with water, H2O at the surface, O and HO and coupled with the other hydrogen, you have 2 OH. So in this way, you have hydroxy on the surface for such low coordination, small specific surface area zinc oxide, and also the other transition metal oxide catalyst. So, and like this, and please check hydroxy surface is formed, but it exists here. So when you add these two equations, multiply by 2 and multiply by 1, and you have summation. You just have CO, 2CO plus O2 and 2CO2. This is the catalysis occurring in this on this surface, and the excited by the hole and electron. So UV visible light. So this is the very, very fundamental, the type of the inorganic oxide in this field, the catalysis. And this is Tuesday, the Dr. Lufti, the talks, the partially, mostly the Tuesday topic was the how to make good paper, but he briefly mentioned metal organic framework, the research trends. And so this is metal organic framework. This is the not in, I suppose not in organic chemistry, the undergraduate or graduate, even graduate course textbook, but this is research trends. I briefly explain what you may already know about by Professor Lufti lecture, but I briefly explain because we partially modified this metal organic framework for our catalyst. So picture is complicated. So I briefly explain so this is titanium. Green ball is the titanium, coordinate with oxygen because titanium all cluster is from here, this hexagonal picture. So it means 6, I think 6. I think 6 oxygen, okay? And this is bridged. This is carbon. I forgot something. This is bridged, and this is benzene and terephthalate, the carboxy, para carboxy, dicarboxy, and I forgot the oxygen bridging, but it should be carbon here. Bridging carbon connected to this cluster. So maybe some are hydroxy. Where is hydroxy? I think top is hydroxy. Please check later. So titanium cluster is forming here. Here it's the 8th cluster is shown. Which cluster is shown here? 12. Here it's with. So this is shown 6 ring. Maybe 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Such ring is shown. So titanium O is forming. This is titanium, just titanium is drawn. But you draw oxygen, make this such kind of ring, and ring exists here, and the ring, we may call it cluster. This kind of ring is connected by telephthalate. So this is inorganic. So this talk is slightly go further, not beyond the scope of Diana-san, but the people are saying this is many inorganic chemists is using this. So let me allow to introduce the topic, because this is organic. So today is not organic chemistry talk, but organic is also to connect together. So metal is, for this case, titanium metal cluster. And organic is connecting metal cluster. Or different type of metal organic framework also exists, and that is much simple. Metal is zirconium ion, just one zirconium ion, and that is connected to organic. Such type of metal organic framework also exists. It's maybe I should explain about from the beginning, but using single metal connected to. But today I'm more research focused, so I begin with my laboratories work, introduce laboratory work. So I begin with this, because this titanium cluster, we choose this titanium cluster rather than single titanium or zirconium, the ion connected to organic, this kind of linker. This is use linker because it connects to metal, or this kind of metal oxide cluster connect. So links. So this is organic part is called linker. And see this picture, and this is, you see this. This is, we would say this is sheet, right? Because this I'm confused. This is something different. Basically, this is kind of sheet like, and this is confusing. I mean, I don't remember that. The sheet like connected to, so this is the benzyl ligand connecting this in plane. We would say this is AB plane. This is axis A and axis B, and AB plane. And C plane is perpendicular this sheet. So this is second sheet, third sheet. So each sheet need to be connected to be stable. This compound, we would say this is inorganic, but this is often called MOF. MOF, the sample. So this sheets are connected by this benzyl linkers. And we chose the titanium oxide cluster because this is something like similar to titanium dioxide, like Diana-san work. So we assume this works in catalysis. This works behave as the or not necessarily photocatalyst. This works as the titanium dioxide surface. Perform catalysis like titanium dioxide. So not titanium single ion. Single ion is not like titanium dioxide, the metal oxide nature, the solid nature. So it's like just ion, single ion. But we hope this works. The like titanium dioxide, metal oxide, solid nature. Okay, so next is we modified and to make this the who was saying the yesterday laboratory we were talking the mix with copper with we read paper titanium dioxide with copper and our we were preparing sample yesterday with the graduate students and for this case the copper is mixed and at this time there somewhat before I talked with one of the graduate students and mixed with this titanium oxide cluster, this green section with copper. So we substitute this parenthesis is lacking the copper to OH6. This gold is copper and O oxygen is O. Hydrogen is abbreviated. So copper to OH, this inorganic linker was substituted for terephthalate. Terephthalate is this black one. So this is basically for catalysis, it mostly do nothing in our case. Maybe sometimes charge trap is possible with the like pyridine ring or something like that. But for this case, terephthalate do nothing. This just stabilize the catalyst, MOF. And in our preparation, so this inorganic linker was substituted for terephthalate, for linking terephthalate between layers. And this was determined by the not X-ray absorption spectroscopy. This is also crystal structure analysis has been done. Lead belt. You may have heard about lead belt analysis, X-ray diffraction analysis, but for crystal has been done in this paper. So it's kind of the inorganic synthesis. And our major interest is for catalysis and how that is works to know, to study, investigate the detail, what is happening is. So this is Dr. Yoshida, who has done this work. And I miss Dr. Yoshida, who already graduated from my laboratory. And this is the result of, so this is CO preferential oxidation. People call it PROX, preferential PR, oxidation OX, oxidation of CO. So hydrogen remain and no water is formed, just CO is removed and CO2 is easily removed from your hydrogen gas. And this is, sorry for confusion, this is not photocatalysis. This is the nearly room temperature, but the normal or thermal catalysis. So it can be repeatedly used. MR is the titanium MOF. And this linker was also analyzed. And I said this is analyzed by X-ray, ray diffraction, crystal structure analysis, but we also use this technique, tomorrow I thought, we can obtain metal, titanium, silver is titanium atom. Gold color is the copper atom. And the distance is obtained. N is coordination number. How many, from seeing from your titanium, how many copper exist? This is the technique, X-ray absorption spectroscopy. Tomorrow I talk. But so synthesis, you need analysis also. That's what I'm saying. And we improved, based on this information, we improved our catalyst to finally obtain this performance. Because catalysis, the performance is essential. Okay. Then, now the students are following well my talk, or most of the student is not following the topic because it is too difficult. I do not know, but I may switch to maybe easy, more familiar topic. So CO2 and global warming and the energy issue. So I think also Indonesia, this is also unsustainable, energy, the issue. I think Indonesia, also you talk often about this. And like Diana-san or the researchers, doctors are working for this such topic. I think so. And so the scheme is the if CO2, this is the carbon cycle. But this is carbon cycle on written carbon cycle. And this is not realized. This is just I wish to do this, but anywhere it's not realized and CO2 is formed. And you increasing. Recently, we can monitor CO2 concentration in room. And my laboratory, for example, but it depends on our operators. It's 600 ppm or something like that. The outside, I do not know. I heard it's 400 ppm recently. So fuel is used for your energy. We need energy. Combustion, CO2 is formed irreversible way. So this is not cycle. This is irreversible one way. You visit somewhere, you do not come back. It's one way. Okay. And round trip is not different. Round trip, you need a ticket to come back to your home. So you visit somewhere, you need round trip ticket. So this talk is round trip ticket. Enable round trip ticket for CO2 trip, and renewable energy need to be used, because if you use the not renewable energy, it's not your return ticket. Thus you can return your home, but your friend cannot come back Indonesia, and you miss your friend forever. So renewable energy, like light, is used. So if this is enabled, this come back, and this is cycle, go and back, round trip. Maybe next page is too heavy. Wait. Next page. Also, essential point is forgotten. Essential point. People tend to forget. To this, enable this round trip return ticket. Inexpensive material. Those do not require extra energy, need to be chosen for the conversion. So if, for example, you use platinum for this, I think it's not a good idea to use platinum here. because who can use your platinum? That's a question. So in total, basically in many parts, the CO2, this cycle should be enabled, not in just in factory or in one, not at your home only. So this is the sustainable future. So inexpensive material is we consider to use inexpensive materials so not include the precious metals. Okay, so this is as the inorganic today's talk, inorganic compounds. I introduce also layer double hydroxide material. This is the, I think it's familiar from your kindergarten, not just in high school or in university. You are familiar with this compound from your kindergarten. This is clay. Some are kindergarten, some are natural, but some are synthesized. So this is clay. That's one of the type of clay, not all the type of clay. So this special point is I think you may be familiar. This is the sheet, so clay sheet, and an ion is between here. So this is somewhat one type of clay. The other type, or maybe major type of clay, is the cation is here, and sheet is anion. Because this clay is cation sheet, maybe cationic sheet, and interlayer. This anion here, this is Navid Ahmad in my laboratory at that time. He is working in Mitsubishi Chemical. He from Pakistan, but he like Japan and working the biggest chemical company in Japan. And this is this is zinc. We made many, synthesized many inorganic. This is inorganic compound. Any carbonate exists. Carbon. This is also special type of. This we call LDH. Special type of the anion. Carbonate is not the organic. No CC bonds. CO3 2-. It's not organic. So this is inorganic compound, Diana-san's scope, today's scope. And we use this layer continues in this direction, the 2-dimensional. And the other layer continues like this starts. So this is clay. And interlayer, the carbonate exists. So similar to carbonate, CO2 and H2 and UV visible light. Methanol was found using this catalyst. This is zinc, gallium, copper, aluminum, relatively cheap. So I say this is the sustainable. And by choosing the catalyst, this is what is interesting in this inorganic synthesis. What is interesting is you can change, you can control the ratio of zinc to copper, amount of copper in your synthesis, or even you can change the anion, interlayer anion to not carbonate and you can increase the copper was essential, so you can increase methanol formation rate by choosing the composition of your catalyst. I will check chat. Not very certificate. Okay. I may check also certificate later. Okay. Then methanol selectivity. So CO and methanol is a product. And here, now I'm sorry, this is the Japanese expression, photocatalyst type amount. This is the old slide, and this is the JPG picture, so I could not change it yesterday. I was talking with the graduate student for their census yesterday, so I did not have time to change these into Japanese, in English. And this is previous slide, and he is in Asahi Chemical, Kawamura. And this is before COVID-19, but he is with mask, even before COVID-19 time. Maybe he caught cold at this time. Okay, so we also, so in organic synthesis or preparation, this type of, but different type is maybe just this one. Bismuth oxychloride. So also including halogen, bromine was, what is that? Bromine chloride, iodine also, iodine. We tried with chlorine here. This is also very popular type of the inorganic compound you studied recently. For example, photocatalysis. And so, well, this is combination of the, Diana-san, I think know well, the combination with palladium, combination of copper with titanium dioxide. And used as film or CO2 hydrogen reaction and CO2 water reaction. The intention of CO2 hydrogen reaction is CO2 water reaction is sustainable reaction to enable to reduce CO2 from irreversibly. So make the carbon new carbon neutral cycle by this reaction, but hydrogen is water spreads into hydrogen and oxygen. So this is part of the reaction of this whole step. So we test first this, and then next step we finally do the total reaction of this. This is how a part of the reaction was tried first. So hydrogen is basically formed from water. We assume that. So, and this is the product. And then I talked nearly 1 hour, so I go to today's conclusion. Not this is last one, but I try to what I wish to talk. Maybe something the very recent critical trend in this field, worldwide trend, not only for my study. It's very big trend in this sustainable solution. I point out this point at these three or four slides, and I finalize today's talk and continue to tomorrow's talk as the final how to say the final our success to explain our final success. But today I partially conclude I point out importance today. And so everything is something you face some problem, and everybody face problem. And so I point out the problem, and this is not my problem. Everybody faced this problem. And so we prepared titanium dioxide, palladium, P25, This is not explained, but this is people said, companies sell this, and this is often, very often used, titanium dioxide. And this was, we were happy. This was good catalyst for methane formation. Methane can be used, commercially used. So by methane, CO2 is formed into methane, and methane is used that make carbon neutral cycle. So it does not increase the total amount of CO2 because CO2 is reversely transformed into methane. So CO2 is once converted. So that makes carbon neutral cycle. So when you consume this formed methane, and again CO2 is formed, this is making neutral cycle. So the carbon dioxide level is constant. That is the carbon neutral cycle. No change. It's something like equilibrium in your chemistry textbook. Okay, and here, and the topic is somewhat more research basis and complicating, but listen carefully. This is the titanium dioxide we made at laboratory and combined with palladium. Palladium may not be very, very good because palladium is expensive, but palladium was good at the time. Okay, methane 5.3. Okay, so we were somewhat surprised because we tried to make very similar titanium dioxide to commercial P25 Degussa company. Company name has been changed, but it's Degussa company. This is not palladium one. So also palladium. This is anyway reaction with water, but we reported trends, but some not just senses analysis needs to be checked. So this is exchange reaction under 13 level isotope labeling. We began test was done because isotope doing label the origin of the carbon. It can be maybe known, but we got more. And everything is not tomorrow. Today, the beginning is very important. So this is exchange reaction, time cost reaction, and 13 CO2 was introduced, this palladium commercial titanium dioxide. So this is adsorption on surface. 13 CO2 gas amount is reduced in time as a function of time because it slowly adsorbs on this catalyst in organic compound. Instead, 12 CO2 evolves. What does it mean? 12 CO2, this is much simple. 12 CO2 is staying on surface. And this reaction of net 1 day, 24 hours, exactly saying 21 hours, this evolves slowly. So this amount was 3.3%. We purchased this 13 CO2 reagent. It contains 1% of 12 CO2. So this 12 CO2 amount was 2.4 micromoles and total amount of 55 micromoles. So it means 3.3% was 12 CO2 at the end of reaction. So this means 12 CO2 was adsorbed on this catalyst. 2.3% of 12 CO2 was adsorbed on this surface and evolved. So this kind of CO2 adsorbed from air affected our catalysis. And due to this effect, this is the time course. This is time, reaction time, photocatalysis time. And this is 13 CO2 formed from, because reaction was done 13 CO2 plus hydrogen. So in our paper, 13 CO formation is shown at this time. I forget to list this paper, the title of this paper. Check my website. And 12 CO formation is not shown. If I cannot show, I can, but much more 12 CO formation curve is not shown. As paper, for most of the people do not pay attention, but it's critical. So then 13 CO2, 0.67 kilopascal. So we use glass system, vacuum system, Pyrex system with pump, vacuum pump. And zirconium dioxide, 0.1 gram, or silver mixed zirconium dioxide. And this is today's topic, related to today's topic, inorganic compound. So this is composition, zirconium, but zirconium oxide was supplied from company, the Japanese company. High surface area one, 100 square meter per gram or something like that. And let me introduce the liquid phase reduction. We use sodium borohydride to reduce silver +1. So by doing that, silver +1 is reduced to silver, metallic silver, nanoparticle, and combined with the carbon dioxide. Okay. And this is, I think, today's final, and continue to tomorrow. But this is time course. See this one especially. This is 13 CO2 and hydrogen was introduced to glass system. In the glass system, our catalyst is set here, 100 gram, 100 milligram. This is gas. Please be careful. This is not aqueous solution. Okay, this is gas. So gas is flowing to powder. This was used as powder, not film. And to the powder, we use lamp. Maybe we can use sunlight, but it depends. Like today, the Japan is rainy and becoming suddenly like autumn-like or even early winter-like. And so today we cannot experiment today, for example. So we use constant light intensity lamp is used for this analysis test. For example, 48 hours, and see this. So using 13 CO2, 13 CO was nominally constantly formed, and minor 12 CO. This is not from 13 CO2. Was from so photo reduction took place in time course. This is pretty simple, but surprisingly, nobody has shown this time course isotope labeled study in time course. I think this is the first report to show as in time course. And nobody means nobody in the world. Human history, nobody has done that. Our laboratory has done that for the first time and reported. Because this is essentially important. This is the direct proof. 13 CO2 is converted into 13 CO2. But why the 12 CO2% is 8.6? When we change the light, full light means UV light and visible light both, from 200 nanometer to 800 nanometer, but also it includes a part of the infrared light, but infrared light do nothing for our catalyst. But we limit the wavelength more than 320 nanometer, means we cut the UV light between 200 and 320 nanometer, the activity decreases because the UV lights, it means UVC lights. UVC light, part of the UVC light is not so hazardous for your skin. But anyway, the UVC light is playing essential role for zirconium dioxide activation, because zirconium dioxide, the energy level is related to energy level of zirconium dioxide. Tomorrow I talk about more about that. It's inorganic synthesis, but the inorganic nature, the physical, solid state physical nature is related to this performance change. And this reagent, 13CO2 reagent, the 1% is 12CO, as I mentioned earlier. So 8.6% was CO2. We have done this experiment repeatedly. So continues, but I suppose many persons so listen, and this is the end of the talk to listen. So CO2 adsorption was strongly correlated to this photocatalysis and behave as the active site. That was known based on this, but in detail, I talk tomorrow. So this is the talk, my talk, Diana-san, I turn off the air conditioner, sweaty in my room, it's too cold. Today is too cold.
Yes, thank you very much, Sensei. Okay, from audience, any question? From here, my student. Okay, Sensei, maybe before question from audience, I will ask. Maybe this is too hard for here for us, especially for our students, because now they are in 5th semester, right? And then in this lecture also, in synthesis of inorganic compound, they learn until now about what kind of method if we want to synthesis of inorganic compound. Also for synthesis in coordination compound. Maybe I want to know, also maybe my student want to know if we want to make some inorganic compound, what method we want to choose method. I tell to them that we have some method like hydrothermal, salt gel, and then sonochemistry, and then also ceramic. And maybe the simple question is what kind of the simple method if we want to synthesis inorganic compound.
Mm-hmm. I see. Good. So Diana-san question is good question, and I understand Diana-san wanted to. I start again my. Wait a second. I start my PowerPoint. My PowerPoint disappeared. Okay, so I come back. Where is my Zoom? My Zoom is very small. Okay, come back. Diana-san, metal oxide. So so Diana-san I suppose teaching the Zorger. Then mentioned Zorger, sonochemical,
Yes.
Zorger, sonochemical, and also plasma,
Hydrothermal.
hydrothermal,
Yes.
and also many recent. And so I suppose Diana-san is teaching in your class and metal oxide. And so one of the reasons I did not start to talk is some of just the surprise from company, and I do not directly synthesize. So that is the reason. And also today's talk was not limited to metal oxide. So, but I explained briefly, as far as I remember, explain this one, like hydrothermal, I think, technique. And hydrothermal, but we add organic compound in your bottle, or I suppose some are autoclave, but many type tried, and for this case, organic was added to cap on. So when grows in hydrothermal in autoclave, we add some chemical to cap. So just adsorb on side of this. So it grows. This is C direction in spheroid. So just the top is drawn here, but in spheroid it grows in C direction. So it becomes like the not spherical. It's like the line shaped one. So this is one modified way of hydrothermal way, and in census point of view, and this is somewhat different. This is organic is included. So this is basically, but also this is, I think, kind of the hydrothermal, but not hydro, because the soluble thermal, I think. Soluble thermal, because organic is solvent, it's synthesized. So the solvent to dissolve this is the what's the name, the benzoic acid or something like that. It is dissolved in organic solvent. So like kind of soluble thermal way, and we would use, if pressure increases high, the autoclave to pressure resistive autoclave to how much, the 200 atmosphere or something like that, and 200. And also, but temperature is just until 200 centigrade or something like that. 200 or 300 centigrade. Autoclave is used. And and this is not somewhat different compound to Diana-san, the mentioned. So because this is hydroxide, not oxide. So this is maybe something specific, but I think in some of the inorganic laboratory or in organic application, this is one of the typical inorganic compounds, clay. And this is, I think, the synthesis is, I think, in some way important in this, in connection to the questions, I think. And this is formed in, this is just something like simple solution and pH control, and grows, the crystal grows in how to say that? Crystal grows in I do not explain it, I think, precisely, but this is something like Zolger. Grows like Zolger. Like Zol is formed as the pH, slight pH change, the seed is growing. So, but not pressurized. In most cases, we do not choose to pressurize. Most of the people do in aqueous solution, and like Zolger, and it grows slowly. So it's heated at 40 centigrade first, then next is 90 centigrade for overnight, and then grows in 1 week or something like that. And the other one is and this is, I said, this is one oxychloride is also as material expected some. I forget to include graphitic C3N4. I forgot to include into here. Experiment was not done yet at this time. I'm sorry for the presentation. I could not find that in the paper, Journal of Catalysis paper, it's included, but at this time, this 3-member talk, it's not has already done. So bismuth OCl, this is synthesized not thermal. The Diana-san's soluble thermal or hydrothermal means I feel it's something pressurized and severe condition, but the relatively mild condition. And so in beaker, I think, and the hydrothermal or soluble thermal, but not in autoclave, this is formed. And graphitic C3N4 is also popular. And graphitic C3N4 is formed from urea, like also beaker, like what way? Hydrothermal way, I think. So I think I'm not very exactly speaking the Diana-san's context, but the traditional metal oxide synthesis, we have not done, and we just company supplied for us. And detail is in paper, the company supply code is written. So the preparation, the hydrothermal or soluble thermal, Zolger is basically described in the supply company, the data sheet.
Okay. Thank you, Sensei. Thank you, Sensei, for the answer. Any question from audience from here, from class? Not yet. Maybe from Zoom. Okay, Anissa Chan, please.
Okay, first, can you hear my voice clearly?
Yes, great.
Okay. Thank you so much for the opportunity. And good morning, Professor. Hello. Let me introduce myself. My name is Anissa Lutfia. I am one of student of Diana Rakhmawaty, Dr. Diana, and she is my supervisor. So yeah, thank you for your explanation. It's really interesting field for photocatalyst, and in my final project in my last study is about also about photocatalyst. So it's really interesting and really good, and it's helped me a lot. So I just wondering about something. First, you explained that the photocatalyst, for example, zinc oxide assisted cuprum, it can be used for oxidation, carbon monoxide to carbon dioxide. And the product, which is carbon dioxide, it can be used to renewable energy, right? Okay. However, some material also synthesized for reduction carbon dioxide to carbon monoxide. And for the same application, which is for renewable energy, also for making fuel and other chemical compound such as alcohol. So it's a little bit make me confused which way is there. And then also please correct me if I'm wrong. So what do you think about this? Thank you for your attention.
Today, so in context to explain the inorganic synthesis, the topics, for photocatalysis and our catalysis and development talk is mixed together. So this is Anissa-san question is the often question for us. The many our students also make this question, and always the students are confused. And so and each reaction. So, for example, so especially CO, I try to explain the CO oxidation, the preferential reaction, because the Diana-san has been working, I think, the titanium dioxide and related. So I wish to pick up the relatively simple the compound zinc oxide, and then so and the react in the point of view of reaction, CO oxidation reaction and CO2 reduction reaction to CO was talked together, and it's very confusing. And CO reaction, that is in hydrogen gas. The application is in hydrogen gas. So 1% CO is often included when the production of hydrogen from in factory. CO is included. So selective CO removal was tried. So that is the reason to oxidize, to remove CO by, but hydrogen and CO, so by non-catalytic removal of CO is supposedly difficult, because it's in liquid nitrogen you cannot remove with CO. With CO2 it's easy to remove. So selective absorption is the other possibility, but in hydrogen, selective separation by adsorption to zeolite, for example, something like that, is, I think, very difficult. So CO selective, but hydrogen remains the same, and CO oxidation, selective oxidation, is in that point in fuel cell. So it's fuel cell before fuel cell. So in Japan, fuel cell, platinum fuel cell is used. It's not cheap, but platinum fuel cell is used and hydrogen is supplied, but this catalyst is needed to remove CO. So this is the reason to oxidize CO to CO2. But the next step, CO2 reduction, sustainable reduction, was I mentioned. This is much more global and much big scope. I think not just in front of the fuel cell pretreatment. This is to save everyone. I try to say if I reduce CO2 globally, and Indonesia CO2 level, as well as Japan, United States, Russia, everywhere CO2 level is decreased, contribute to human, for the people. That's the intention. So latter part is the major, much more major the explanation for me. But today I include the selective CO oxidation. So it's yes, often. And also Japanese student, why CO2 is formed? Because CO2 is not very good. So, but CO2 is removed. And so I may say the CO2 is removed and then treated with our catalyst into methane. And recently we can make it into ethylene or propylene. We can use, or methane. We can utilize that in many possibilities. We have possibility. Using our catalyst, CO2 is photocatalyst, transformed into methane. Not that only, tomorrow I talk about that. Or when you visit us, maybe we will talk. And you may have review paper under construction. You have review paper. We may talk about that also. But CO2 photocatalytic conversion into methane or ethylene, propylene, these saves the many problems. That's a major thing I wish to talk. But selective CO oxidation also has certain importance for in front of fuel cell, and that is used in different ways. So basically, to separation, CO separation, to remove CO, to save your platinum, because fuel cell is very expensive, like it costs like car. But it's used same catalyst, nearly same catalyst. The platinum is used, so it's something like car. So fuel cell car, for example, fuel cell car, you need this kind of catalyst. You need to save because it's expensive. Fuel cell car, you need to use it for not just 1 year. You need to maintain your platinum. So our first part catalyst is needed. That's the major difference.
Okay. That's really clear. Thank you so much for your explanation. And thanks for the opportunity, Ibu Anna.
And Anita-san, you were not in class today, in different place?
Yes.
I see.
Yeah, I'm in a different country.
Oh, different country?
Different country?
Yeah, different city.
Different city. Oh, sorry. Different city.
Country in Indonesia. I see.
Country in Indonesia.
I'm so
Did
sorry.
you say country? Indonesian?
Yeah, city. I mean city.
Okay.
Yeah.
Okay.
So sorry about this. I'm so nervous right now.
Don't be nervous. Relax.
Okay.
You can meet.
Thank you.
You can meet Diana-san.
Yeah, I am different country with you, maybe.
Okay. Good.
Yeah. Okay. Thank you.
Thank you.
Thank you so much for listening.
Leaving.
Thank you. Thank you, Ivana.
Yeah. Next question. Thank you. Dr. Irwan, please open cam. Yes, Sensei, Dr. Irwan also graduate from Omori. Yes, Omori University, Japan.
Correct me. I'm graduate from Hirosaki University, Sensei. Okay. My name is Irwan Kurnia, Sensei. To introduce myself first, my name is Irwan Kurnia. I'm now working with Diana Sensei, also in Universitas Pajajaran. So I want to ask, maybe it's out of the scope of from today is around about the synthesis, but I want to ask about your opinion, Sensei. Is about MOF material for oxidation, photocatalysis oxidation reaction is like that. So how about your opinion? Because in the MOF structure is contain organic compound, right, Sensei? So sometimes other researcher also want to oxidize the organic compound also. So is it how to say? Is it possible that the MOF structure will be collapsed, or it will be maintained? It is
Good question.
itself. So it will be maintained during the reaction or the photocatalysis process. And the second question, or maybe it is the is like request for me for the next, maybe the next meet is for the analysis, right, Sensei?
Yes, analysis.
Yeah, the analysis. I want to request about the in situ FTIR, because it's the advanced analysis, right, Sensei? The in situ FTIR or in situ exaf. So if you don't mind, could you to how to say show the schematic or show the picture about the in situ FTIR? Because until now, maybe if we want to do the in situ FTIR, in Indonesia is not available in everywhere for the in situ FTIR. So maybe if you don't mind, so you can could you share the picture or the schematic arrangement, so we can learn from you. Maybe that's all my question and my request. Thank you.
Thank you, and good question, and MOF question, and I think good points. And for our CO oxidation, the CO gradually decreased, and it repeated, and CO in corresponding to CO molar amount, CO2 was formed. Maybe I can show, but maybe take time, but I will show that. This is like a CO decrease and CO2 formation, but this is something different mechanic. This is commercial, not commercial. The reference, the catalyst in reference, and maybe some problem. CO2 adsorption to cerium oxide, not our catalyst basically, but our catalyst is more like the more amount was in accordance with the reaction. So this terephthalate seems relatively stable, but I totally agree your suggestion, and I do not like to use this, the MOF for CO2 photo reduction. But I see many paper, but I'm very nervous to exactly the same point as you point out, for example, the possibility of the reaction of this terephthalate, the parts in the photocatalytic reaction test. So I'm very nervous to utilize this, the MOF in CO2 photo reduction or related catalytic tests. And so also, so we do, and also to avoid such the program, the self-decomposition. We prepare to check the isotope labeling, 13 CO2 or D2O for water, D2O and H2 reaction, the deuterium we labeling or 13C labeling, we can distinguish from the self-decomposition. So I agree, but for this case, it's quantitatively the reducing and evolving. So hopefully it's okay. And second question is also, and I was, yes, I've not prepared exactly the tomorrow's slide, but I'm thinking to, and also, yes, the in situ exercise also we are doing, and also FTIR is the, so exercise sees the, for example, the CO2, no, not CO2. FTIR, it sees the how CO2 transform to, for example, bicarbonate or formate or maybe CO. Or recently, to when methane is formed, the CH2 or CH3 has been also monitored. So that is done in situ, and in combination, in situ exercise, during photo reaction is the nickel. For example, today I talked silver, but the nickel or cobalt also good for methane formation or ethylene or propylene formation. So exercise is important to the nickel, the state of nickel or silver or cobalt analysis. So I was planning to talk about that tomorrow. So I can talk about this. I hope to explain the, and FTIR is but I make the glass system to make it in, how to say that, the in situ, so maybe the Diana-san, in your laboratory with Diana-san, so FTIR itself is purchased and you can fabricate the in situ system. I think. If you do not use yet, I think it's interesting for your study.
Yeah, thank you, Izumi Sensei. Yeah, because why I asked about the in situ FTIR, because we just use the FTIR is just for how to say, is like using the other accessories is like ATRs, can say, and the FTIR also, that FTIR also not use the high sensitive of the detector. So sometimes if we want to analyze the, how to say, like a small amount of the how to say, a small amount of the compound on the surface is not detected, Sensei. So I want to, so that's why I asked to Izumi Sensei, if you don't mind about the to show the schematic or to show the arrangement of the in situ FTIR, so we can, how to say, see and learn how to
I see.
say, to in, yeah, is to how to say, to use it in
I see.
Pajajaran. It's like that.
I have not used the ATR setting, and I was wondering so for example, photocatalysis, light is introduction in the ATR setting,
okay.
maybe to the diamond, below
Ah,
diamond.
okay.
The-
Diamond. Okay.
So I'm not quite sure about that point. And also, I think your comment is the is related to very essential point, I think. And because I'm also considering, so what you see in the FTR during the test, for example, it's not necessarily be the product. I mean, so you said small amount, very, very small amounts. And but unfortunately, maybe tomorrow I talk about what I see, and it
okay.
not necessarily be the intermediate.
Okay. Okay.
So maybe in that sense, I cannot be the best describe what is happening. So also, but I try to adjust that point. We also calculate the reasonable pathway to, for example, to CO2 to methane, or CO2 to tomorrow maybe until methane. We are working on also ethane. So maybe theory is help. So, but tomorrow I talk a part of theory we study to maybe to answer part of your question. You mentioned small amount of intermediate. Maybe
Okay,
small amount may be difficult to see.
Okay.
But
Thank you very
FTI,
much. Okay, Sensei, thank you very much for
Thank you.
the nice talk, Sensei.
Yeah, thank you for your essential question. Diana-san, I think one of your colleagues is the handmark. Yeah.
Yes, sir. I don't know why. Buana, we still have time for question. Maybe you mute your
Okay, please.
device. Okay.
Okay, please, Dr. Yuda.
Yes.
Yes.
Okay. My name is Yuda, sir. Yeah, Professor. My name is Yuda. I'm working in homogeneous catalysis, which is different opposite on your catalysis process. You are doing heterogeneous one, but I'm doing homogeneous catalysis when using organometallic catalysis. But I would like to ask to open the mindset for students, maybe this simple question about the preferences of choosing the metal center as the catalyst for heterogeneous catalysis, your process, your type of reaction, because commonly in our laboratory who is working on metal oxide catalysis maybe only Dr. Diana, and commonly in students working the students working on titanium oxide as the catalyst, and then you are using zinc oxide, which is open minding the students that there are type of metal oxide that can be used for different purposes. I mean, my question is about the preferences of choosing different type of metal oxides for different purposes. So what is the preferences of choosing the different type of metal oxide, specific metal oxide? This is the question. So
to choose, so you mean zinc, how we choose zinc oxide, and
yes,
how we choose zirconium oxide?
Yes.
Or titanium oxide?
Yes.
Good question. This is rather than we choose, we try.
Oh, you
we
try.
And for the first application, the reaction, zinc oxide was good in the test. And latter test, the latter part of talk, zirconium dioxide was talked. Zirconium dioxide was the good. But the latter part, it's something complex. And we also, like the doctor, the Umpat some question, we wish to verify reaction mechanism, and the introduced CO2 is really reacting to CO. So labeled 13 CO2 was checked to form 13 CO or 13 methane. And the result is we test many titanium dioxide, zirconium dioxide, zinc oxide, and also bismuth OCl. I showed today LDH, all these things was tried. So it's not, unfortunately, not like choice. It's something, the result was the zirconium dioxide. But we are aware we should try more. We should find better one, even better one. So at this point, zirconium dioxide is good, but we would try something like more recent one. So in like homogeneous catalysis, maybe slightly homogeneous catalysis, you would synthesize the catalyst and more focus on the one catalyst possibly in detail, tend to focus on more in detail, but maybe in homogeneous catalysis field also you screen, you try to find a good catalyst.
Yes, exactly.
Yeah, so it's something in that sense. It's similar to rather than screen, but try, but at least try several catalysts. For this case, inorganic compound, but combination composite is tried also. So so this is a result, and maybe not choice.
Yeah. Okay, sir. Because in homogeneous catalysis, sometimes you are dealing with or modify the electronic properties using more donating ligand or weak donating ligand, and sometimes we are dealing with steric effect as well.
Yeah.
Supporting ligand. So I'm asking this question of maybe it also happen also in your working system using zinc, which are fully filled the orbital, and the titanium is not fully filled the orbital electron. So maybe, but so this is kind of trying to repeatedly screening the best condition, like that.
Yeah. So it's similar to the change of the ligand or substitution or the steric effect, the control. So such control. Tomorrow I partially talk tomorrow the feedback, but it's something like the combination of, for example, zirconium dioxide with the metal. So in today's context, the cheaper metal, first row metal, and the size of the metal, and the oxidation condition of the metal. These are, in some sense, similar to the such control, fine control of the ligand of your metal center in homogeneous system. Also, so tomorrow I talk about, and in some sense it's that has the similar investigation is included. I can talk tomorrow.
Yeah. Thank you, sir, for your explanation.
Thank you for your question.
Yeah.
Okay, thank you, Dr. Yuda, for the question, and then Izumi Sensei for the answer. Any question for audience? Dr. Yuda, finish from here. Yes, Georgia. Angel. Yeah, this is a Sensei question from my students. Okay, please.
Thank you, Sensei, for the opportunity. Before, I'm sorry if I'm lost, but I got several questions. I'm noticed that catalytic for the fuel is
Please stand up.
oh,
Berdiri ya.
yeah. I'm sorry if I'm a bit lost, but I got several questions. I noticed the catalytic for the fuel. Is it impact to fuel only or also to the machine? And if it's interact with metal, can it be any metal or a specific metal? And can it make the metal life longer? Thank you.
I did not really catch you mentioned the metal to reactant, the coordination. Diana-san, Diana, sound was
I'm
not,
sorry, San.
sound was
May
not.
no. Direct, please direct. Maybe it's close here. Please here.
My question is that the catalytic is used for the fuel, and what impact to the fuel, and if it's impact, is it impact to the fuel only or also to the machine? And if it's interact with the metal, can it be any metal or a specific one? And can it make the metal last longer? Thank you.
For fuel. Metal for fuel. Yes.
Tadi yang katalisis buat ini kayak bahan bakar. Jadi impactnya ke bahan bakar itu apa? Terus ke bahan bakar aja atau ke mesin? Kalau ke mesin kayak bisa bikin mesinnya tambah.
Maybe in this one depend on your presentation before. You use the metal for fuel, right?
Metal.
The question is, the question is impact or impact, right? Impact for machine if we use for example for motorcycle or for car. It wait a moment.
Impact of the catalyst.
I think it's better to see in the chat box. Say, I'm sorry.
Impact of the catalyst.
Yes.
The fuel. Does the fuel have a good impact to the machine? Does the fuel have?
If we use the catalyst.
The catalyst.
Yes.
Does the fuel have a good impact to the machine? Machine of the our apparatus mean? The fuel. The fuel. Or maybe. Do you mean fuel cell? Fuel cell?
Yes. Fuel cell. Yes.
I think you were saying
Maybe
fuel,
this is for
fuel from the photocatalysis. I see. Fuel from the photocatalysis. Okay. Fuel from photocatalysis is the general fuel. So it's like a natural gas from natural gas in Indonesia, I think. You have natural gas in Indonesia, I think. Yes? I think so you have enough natural gas. So you do not need, but the Japan, not so much natural gas. So natural gas from photocatalysis is good. Maybe it's good for Germany. They do not need natural gas from Russia. It's something like this. And the natural gas, methane is, we can make from photocatalysis, pure methane can be formed. So it's same as the natural gas in Indonesia or Russia. People do not use natural gas from Russia, I think. Indonesia, I do not know, you use all the natural gas in your country or you export, but its fuel is same impact to machine, same impact.
Okay, thank you, Sensei, for the answer. I think time is over because this class also will use, and then our student also will continue the next lecture.
Okay.
Before we closing this lecture, would you like to open camera for all participants? And then also, Sensei, I will tell you today, I think it's special day. Why? Because all of my students use traditional clothes, right? We name it batik. Okay, please come, Oji-san. Oji-san, please come here. Sensei, I will show you. Di sini ya? Here. Please come here. Here is our traditional clothes. This name batik.
Batik.
This name batik. This is for men, and then also for women. Also, please come here. Please come here. Yes, today a special day because all of my students use this batik. Also, in next after tomorrow, maybe I will give some batik for you, special gift. This is with love, with love for our department. I will give you traditional clothes. Okay, Oji, thank you. And then for the last, we will take a picture. Maybe the student standing up. Standing. Please stand up. Ya, berdiri aja ya. We will take a picture for the last. Also, all participants in Zoom, would you like to open camera? And then also I would like thanks to all participants, my friend from Universitas Jambi, Queen Sunan Gunung Jati, and then Polytechnic Bandung, and then also friend from STT Wastu Kencana. Thank you for joining in the lecture. Okay, for the last, Bu Yusi, yeah. We will take a picture. One.
Students are better.
Oh, yeah, sit down. Okay.
I will start to take a picture. Please open the camera. Then I will count 1, 2, 3. For slide 1, please prepare. 1, 2, 3, smile. Wait a moment, please.
Ceria.
Wait a moment. I will take the second layer. 1, 2, 3, smile.
Cheese.
Okay, thank you.
Thank you, Dr. Yusi. Thank you, Izumi Sensei, and all participants, Pak Irwan, Pak Yuda, Dr. Yusi, and then also Prof. Tri Mayanti, Prof. Iman, Prof. Ati, maybe still here. Thank you very much. Sensei, maybe certificate I will give you tomorrow. All right?
Tomorrow.
Thank you, Bu Deska. Yoroshiku nagaishimasu. See you tomorrow.
Thank you for
very
your
much. Assalamualaikum warahmatullahi wabarakatuh.
Diana-san, thank you for your organization.
Bye-bye. See you.
See you.
Say bye-bye.
Thank you very much, Sensei.
Thank you. This.
Ya, model. Terima kasih semuanya. Thank you.